Right, we're going to move on to second order differential equations. I just want to start by considering a first order differential equation, and then we can extend the ideas. So this is a bit similar to what we've been doing, except this one equals 0, it doesn't equal a function of x. And you can solve this by separating the variables, so that dy dx is equal to minus b over a y, and then that will end up giving you the integral of 1 over y dy is equal to the integral of minus b over a dx when you separate the variables. And so ln y is equal to minus b over ax plus c, and then when you do e to the power of both sides, I'm assuming you're okay with this bit really, but I'll go for just this one. So plus c, so that's e to the c times e to the minus b over ax. So we can write that as a e to the minus b over a x. And then minus b over a is a number because b and a are constants. And so we can replace minus b over a with m. And I've just written that as for some m, because this is the general solution to this first order differential equation. And what we can do is just extend this into second order equations. So I'll show you what happens with that. But I'm trying to think if this will work, doing it this way. If I wrote this as, just to show you, am plus b, so m is kind of representing dy dx, and b is your coefficient of y. This will make sense in a minute. I'm not sure if this is going to work at this stage, but and we're setting that equal to 0, then m is minus b over a, but we'll mimic that with the next one, so don't worry if that feels a bit confusing. Right, second order ones. So now we want to consider a lots of the second derivative plus b lots of the first derivative plus c is equal to 0. And I'm going to call that equation 1. And we know that y equals a e to the mx was the solution to the first order one. So what we can sort of do is think, well, is this going to be a solution to the second order one? So we're going to let y equal a e to the mx, so that when you differentiate y, you get am e to the mx, and when you differentiate again, you get am squared e to the mx. And so if we substitute that into 1, and see whether this is a solution. So you get a lots of a squared e to the mx plus b lots of a e to the mx plus c lots of a e. Sorry, I forgot a y, I've just realised. Can we put a y on there? So it looks a bit like the first order one. C a e to the mx equals 0. And then we can pull a e to the mx out as a factor. And we are left with am squared plus bm plus c is equal to 0. This bit here, the a e to the mx, cannot equal 0. And this bit here, the am squared plus bm plus c, we'll do a lot of work with this, so don't feel like you need to take it all in straight away. This is called the auxiliary equation. And so if m is a root of the auxiliary equation, remember a, b and c are constants. So if m is a root of am squared plus bm plus c, so that'll make that bracket 0, then y equals a e to the mx is a solution to 1. It should make sense. And if you think about what I said here with this with this am plus b, what we've got going on here is we've got am squared plus bm plus c. That's your auxiliary equation, and a e to the mx is a solution to 1 if m is a root of the auxiliary equation, which is actually exactly the same as what happened with the first order ones. The problem is, well, not the problem, but we need to extend this slightly, because quadratic equations either have 2 roots, 2 distinct roots, 1 repeated root or no roots. So we need to look at those 3 cases separately and just see what we can do with the solution set, just whether we can extend it a little bit beyond what we've got going on here.